Yes, children. Let us move further in P block elements. Elements of second period can show a maximum covalency of 4. Second period, as soon as you see, there are only 2s and 2p orbitals. Now this is 1 plus 3, that is equal to 4. So maximum covalency that is shown is 4. Covalency means what? Covalency is nothing but the number of bonds that a central atom makes with the surrounding atoms. That is only 4. It can bind with only 4 different atoms or groups. Why? Because they do not have d orbitals. So they cannot expand their covalency. They cannot make more bonds beyond 4. So you will find boron at the maximum exhibiting itself in BF4 minus, BH4 minus. Whereas aluminium can exist in AlF6 3 minus. Now look here. Here the coordination number is 6. Here the coordination number is 4. Here the coordination number is 4. So that is nothing but covalency. The number of fluorine that it makes bond with is 6. So that is what you call it as covalency. Now in the case of carbon can bind only with 4 chlorine atoms, so Cl4. Whereas silicon can bind with 6 fluorine atoms, so it is SiF6 2 negative. Same way, nitrogen can exist only with NF3 or at the maximum NH4 positive. But phosphorus can exist as a pentachloride. Nitrogen can exist only as a trihalide. You have NCl3, NF3, but you have PCl5. Okay, so here phosphorus is showing pentavalency, whereas nitrogen can show at the maximum only 4. It cannot go beyond 4. That is in the case of ammonium, you see 4. Okay, now these d orbitals, presence of d orbitals, how do they help? Let us see. Now there is a question, CCl4 does not get hydrolyzed, but SiCl4 can get hydrolyzed. Why? What is the reason? Now let us explain why SiCl4 gets hydrolyzed. Now this is SiCl4 structure, and you know very well that there are empty d orbitals in the case of silicon. Silicon is having 284 configuration, so you have 3s2, 3p2. So once you have entered the third shell, that means d orbitals are also there, though it may be empty. Now when water is added, the lone pair of electron on oxygen of water may get into the empty d orbital of silicon and expand its covalency from 4 to 5. Look here, 1, 2, 3, 4, 5. Now it is showing pentavalency. Its coordination number is 5. Now once the water gets associated with silicon, then what happens? One HCl, it breaks away and tries to escape. Now when this HCl escapes, then this OH comes in the place of Cl. So you have SiCl3OH. So one Cl is replaced by this OH. Again it has come back to its original form, that is tetravalency. Now again one more water can react with it. Same way it can increase the coordination number to 5, and again one HCl, it is escaping from the medium, and one more Cl is replaced by OH. So like that, each and every chlorine, first by expanding the covalency, it can get replaced by OH. That is why you say SiCl4 plus water gives you SiOH 4 times plus 4HCl. So because of the presence of d orbital, SiCl4 gets hydrolyzed. But in the case of CCl4, since there is no d orbital with carbon, it cannot expand its covalency and there is no reaction of CCl4 with water. Okay, so this is the reason. So what you have to say, because of the presence of empty d orbital in silicon, the lone pair of electron on oxygen of water can get associated by expanding its covalency due to availability of empty d orbital, right? Whereas in the case of carbon, since d orbitals are absent, they are not present, it cannot expand its covalency and it will not get hydrolyzed. This is the reason. Since carbon does not have d orbital, it cannot expand its covalency and thus does not get hydrolyzed, whereas silicon has. Okay, now let us see another question. Down the group, you know very well that ionization energy decreases because with increase in size, ionization energy will decrease. Now, why is it that the ionization energy of gallium greater than that of aluminium? Why? Gallium is having a configuration 4s2, 3d10, 4p1. So basically outer electronic configuration is 4s2, 4p1 and there are 3 valence electrons and this 3d is along with the third shell. In the case of aluminium, you are having 1s2, 2s2, 2p6, 3s2, 3p1. There is no 4s. 3d is there but it is not filled, it is vacant. Now, due to the poor shielding of these 3d electrons, in the case of gallium, I told you already, because of poor screening, outer electrons experience nuclear attraction. Due to diffused orbitals, d and f, they are diffused. So they show poor screening effect. With the result, the outer electrons experience nuclear attraction. So here, due to the poor screening effect of 3d electrons in gallium, the outer electrons are held strongly by the nucleus, because of which, because here this gallium is having a nuclear charge of 31, proton number is 31, is it not? Greater nuclear charge also and poor shielding also. Both the things have given rise to a condition where the ionization energy is increasing. Is that clear? Gallium की ionization energy aluminium से थोड़ा सा ज़्यादा है, not much but a little, right? Now the same question you have already studied in periodic classification also, and again I have told you here. Okay, now let us see a few more questions of this type. All reasoning questions you will find in this P block and S block. Now here, as we move down the group, the stability of lower oxidation state increases. Why? This is due to inert pair effect. I have explained this clearly to you, so you must be knowing this. Down the group, the stability of lower oxidation state is more. If at all a question comes, this is due to inert pair effect. Then, Ga plus and In plus, these salts, they undergo disproportionation in aqueous solution. Why? Why so? Now first of all, remember where is gallium and indium. You have boron, aluminium, gallium, indium, thallium. This we have already seen. Thallium exhibits only +1 oxidation state because of inert pair effect. Now we are talking about gallium and indium, which are above thallium. So they will preferably show +3 rather than +1. Only this will show +1 instead of +3. So these salts, why do they undergo disproportionation? Because in the case of gallium and indium, +3 state is more stable than +1 state. So it disproportionates. How? This GAX, where it is showing +1 oxidation state, what is disproportionation? The same species in a particular oxidation state, that will show a higher oxidation state as well as a lower oxidation state. This is what you call it as disproportionation, right? So +1 is getting increased to +3 and +1 is getting reduced to 0. So this such a reaction is called as disproportionation. The same species, the oxidation state is increased as well as decreased. Okay, such a reaction is called disproportionation. That is, there is more both oxidation as well as reduction of the same species. This is disproportionation. Okay, now come to the next question. BF3 and AlCl3, they behave as Lewis acids. Why? Now here, boron and aluminium both have 6 electrons. With the result, what will happen? They have the capacity or tendency to gain a pair of electrons. Now, what are loose acids? Loose acids are electron pair acceptors. Please remember, loose acids are electron pair acceptors. So, if the central atom is having only 6 electrons, it will have the tendency to gain 2 more from any donor atom. So, because the central has only 6 electrons, that is deficient in 2. Octet is more stable. It is having only 6. That means it is deficient in 2. So loose acids are electron pair acceptors. To complete their octet, they accept a pair of electron from donor atoms. That is why they behave as loose acids. Right? Okay. Now let us come to the next question, that is, show that Al2o3 is amphoteric. This you have studied in 10th class also. It reacts with base as well as acid to give the corresponding salt and water. Now with NaOH, it is giving you sodium meta-aluminate. This is an oxometallic salt. Okay, such salts are called as oxometallic salts. And with sulfuric acid, it is forming aluminium sulfate. So it is reacting with both base and acid. So it is showing amphoteric nature. Okay. Another important question. We can store nitric acid in aluminum containers, but we cannot store NaOH. This is again an important question. Why? This also you have seen in 10th class. I don't know how far you remember. Now, over aluminium, you have a passive layer of Al2o3, which restricts further reaction. Okay? So, because this aluminium is having a layer of aluminium oxide over it, what happens because of that? Due to the presence of passive, the Al2o3 layer is passive. Passive means it is inert. Passive oxide layer over aluminium. This layer prevents further reaction with HNO3. HNO3 is an oxidizing agent. As soon as it comes in contact with Al, it forms a Al2o3 layer. Even then, this aluminium, whenever you keep it open, an oxide layer is formed over it. So whenever nitric acid comes in contact, the oxide layer which is fixed over it will not allow HNO3 to react with metallic aluminium. See, this is the aluminium metal, this is the aluminium oxide layer, and over which HNO3 you are adding. So this layer will prevent reaction with the layer below it. This is the metallic layer, this is the oxide layer, and this is HNO3 layer, right? But with NaOH, it is reacting, liberating hydrogen gas. Since it is reacting with NaOH, you cannot store NaOH in it. Aluminium की container में छेद आ जाएगी. You cannot store NaOH because it is reacting with NaOH. But with HNO3, the passive layer is not allowing HNO3 to go penetrate through the oxide layer into aluminium layer. Okay, so it prevents reaction. Right? Okay. Now let's come to the next question, that is, loose acid character of boron halides decreases in this order. Bi3 is more acidic than BBr3, than BCl3, than BF3. So BF3 is having the least loose acid character and Bi3 is having the most loose acid character. Now why? Now you find that since boron is associated with fluorine and fluorine is highly electronegative, you may expect this BF3 should be showing most loose acid character. Right? Since this atom is electronegative, so loose acid to electron pair acceptor hai, so this unit should be accepting a pair of electron much more readily than all others, because these are all associated with less electronegative halogen atoms. But why BF3 is having least acidic character? That is because when you show this BF3, let me show here. See, this is your BF3. Okay. Now, in the case of boron, it is having a configuration 2s2 2p1. So 2s, 2 electrons, and the p orbital is having 1 electron. This is ground state configuration of boron. Now when it combines with fluorine, it goes to an excited state where the electrons are getting unpaired first, and you have 3 electrons. Now these 3 will undergo sp2 hybridization. This is a boron, and these sp2 hybrid orbitals will overlap with the 2p orbital of fluorine. This is what is taking place. Now there is one p orbital of boron which is vacant, and that vacant unhybridized p orbital will remain perpendicular to the plane. Now this is planar. Is that clear? So this p orbital which is vacant, that will remain like this over this. It will remain perpendicular to the plane. Now surrounding fluorine atoms, they are having a configuration of 2s2 2p5. Now 2p5 means you have 1, 2, 3, 4, 5. This p orbital is overlapping with the sp2 hybrid orbital of boron, and it is forming bf bonds. Now there is a paired electron, and here again another paired electron at the p orbital. So what happens? Any one of the fluorine atom, uski filled p orbital, this is filled p orbital of fluorine, this may overlap with this vacant p orbital of boron. This is also p, and the electrons which are present in the fluorine, they are also p orbitals only, is it not? So the filled p orbital of p may overlap with the empty p orbital of boron. With the result, what happens? This boron will lose the tendency to gain a pair of electron, because surrounding atoms ने ही उस vacant orbital में 2 electron दे करके उनको satisfy कर दिया. So boron will lose the tendency to gain a pair of electron from any other atom from outside. जब internally वो satisfy हो रहा है, ये बाहर से लेने के लिए restrict हो जाएगा. Is that clear? That is why the acceptance of a pair of electron by BF3 is restricted. It is less. So you say BF3 is having less Lewis acid character. Is that clear? Whereas in the case of BI3 or BBr3 or BCl3, you will find this chlorine or bromine. Chlorine is having 3p level. Bromine is having 4p level. Iodine is having 5p level. Now this 3p or 4p or 5p overlapping with 2p of boron, it is very ineffective because of energy level difference. So this kind of the 2p electrons of fluorine overlapping with the vacant p orbital of boron, this is what you call it as back bonding. This is what you call it as back bonding. That is पीछे से किसी ने उसको satisfy कर दिया, बोरॉन की vacant orbital को fill करने के लिए पीछे से अंदर ही अंदर एक एटम अपनी इलेक्ट्रॉन्स को दे करके उसको satisfy कर लिया. So this is what is called as back bonding, which is not there in any of these three. So because of back bonding, BF3 shows less Lewis acid character. Okay.